And as Tony told me, she's really, she wishes she had Silvio's accent, but she's Italian too. In origin, at least. Tony is a professor in Columbia University after many years in the University of Toronto. And Tony's research area is proof complexity, complexity theory, but he's done work in many, many different things, in fairness and in other works, and I'm at awe. And she's also been a visitor to Simons Institute several times, especially she was attending my first year. She was there and we became close friends, and I'm very grateful for her friendship also. And Tony's really incredibly versatile. It's been recognized in many ways, and I'm looking very much toward her talk, which is about replicability, pseudodeterminism, and proofs. So please, Tony.
Thank you. Can you hear me? I'm all mic'd up. Okay. It's really a privilege to be here. I'm going to just start by saying that I'm talking about replicability and pseudodeterminism proofs because I feel like when I associate this big, these different research areas, when I think about them, I think about Simons Institute and being in Berkeley. And this would not have been replicable without my many collaborators, and the main ones related to this work is Shafi and Russell, Max Hopkins, Rex Lee, Jessica Sorrell, who are students of Russell's and probably other people's at UCSD, and Rahul Santhanam. And unlike Silvio, I didn't time things, so it's a good chance that I will, like usual, not get to my last slide. So I decided that I would actually start with my last slide. So you can leave after this one if you want. Does everybody do that too? Like you just forget the end? Anyways, so the end is I wanted to say that the first time I ever came to Berkeley was about 15 years ago. And my daughter said we were ruining her life. We came here on sabbatical. And I was firmly working in lower bounds and circuit complexity and proof complexity. Didn't know much about anything else. And I got introduced to the definition of differential privacy from Microsoft Cynthia Dwork, and then led to doing research in it. And then when I was very, very lucky, and then about 5 years later, the Simons Institute was born. And I think I'd probably speak for everybody. It was just an amazing game changer, both I think for science, but also for me personally. It was just so wonderful to come to so many different of these programs and get to interact with all sorts of people and learn about really cool ideas. And the one on lower bounds, which Shafi mentioned, she introduced me to the idea of pseudodeterminism, and I latched onto that too as another just beautiful definition. And then that led to this notion of reproducibility, so kind of using that idea of pseudodeterminism in the context of learning. So that's what I'm going to talk about today. And I thought about going backwards in the spirit of Steve Cook, who would always sleep through the whole talk and then somehow wake up at the very end and get to the open problems. But I think I won't be able to carry that off, so I'm going to actually go from the beginning. But anyways, I hope I get to this last slide. So I'm going to start with pseudodeterministic algorithms. So let's say so it's a really interesting concept just for problems that are search problems. So by search problem, I mean, there's an input of length n, and could be more than one solution. And we're going to consider search problems that are easy for randomized algorithms. So some examples of important ones are explicit construction problems, like given n in binary, like given n 1 to the n, you want to output a graph on n vertices that's an expander graph. Another example, number 3, very similar to some extent, is again, given n in unary, you want to output a function with a truth table of length n, so it's a function on log n bits that's hard, that can't be computed by small circuits. Another example is finding a prime given a number n in binary, now output some prime that's bigger than that number. And these are examples of problems, expanders, for example, in find hard, where you can just guess you can just pick a random graph, or you can pick a random truth table of a function, and it's with extremely high probability going to have the property. But the question is, can you actually pinpoint a specific one? In another example, this might look a little bit different, but you could start with an unsatisfiable, say 3CNF formula, and let's say it's highly unsatisfiable, so it's a random one. And let's say that by highly unsatisfiable, I mean that there's no assignment that satisfies more than like, a constant fraction of all the clauses. And given an input alpha, which is an assignment to the variables, you want to output a violated clause. And here I'm thinking of a decision tree model where you're allowed to query the values of a variable, and you want to know how many variables you have to query before you can find a violated clause. You can pick a clause at random and check the variables in it, and with high probability, if you pick a few clauses at random, you'll find one, because we were promised that it's highly unsatisfiable. But again, the question is, how hard is it to locate a particular one? It's easy for randomized decision trees by the argument that we just gave. It's hard for deterministic, and the notion of pseudodeterminism is about whether you can output, solve any of these problems by outputting the same solution, but somehow using randomness to do that. Does that make sense? So for these problems, these are all, the random algorithm exploits the fact that there's many good solutions, so you can just pick one at random. But we want to ask, this question was asked by, I think the first paper, and I forgot to write the reference. What's the first paper? That's what I thought. So Gotch and Goldwasser is the first paper on this. And the question was, what if the randomized algorithm was required to output the same solution almost all the time? So this gives the definition that an algorithm is row pseudo-deterministic for some search problem if for every input X, there's a fixed Y such that Y is a good solution for the input X. And moreover, the probability over the randomness of the algorithm that you output that good Y is high. It's at least 1 minus rho. Okay. And the question is, is it easier to solve search problems pseudo-deterministically rather than deterministically? In other words, sometimes it's very hard, we think it's very hard to come up with explicit constructions of things, even though lots of them exist, but can we somehow use randomness to find one that's close to, we think of pseudo-deterministic as close to deterministic because you're pinpointing a particular solution, but maybe with the help of randomness. Okay, so just quickly, turns out find expander is in P. We now have explicit constructions of that. Maybe that's an important call. And find prime, there was some progress on this. There's now a sub-exponential pseudo-deterministic time algorithm. So an algorithm that does find a prime and it finds it in time. I'm lying a little bit, but it finds a prime under certain conditions faster than the best known deterministic algorithms. And find hard, this is still open. And the last example, which is not about polytime algorithms, but about the query model decision trees. Here, we proved about a year ago, this was with Shafi, Russell, and Rahul, we showed that pseudo-deterministic decision trees require square root of n depth. So in other words, it's hard. And interestingly, the proof of this, it's easy to get a bound of like n to the 6th or n to the 4th, but it seems we had to go through proof complexity to get this lower bound, and it's still open to get the optimal omega. But we think the answer is omega n lower bound, although this is tight for quantum decision trees. So it's an open question, and also would like to find a simple proof or like a straightforward proof. And you can, if you don't want to think of this problem, you can think of the promise problem of you're given a string and you're promised that it has at least n over 2 ones, and you want to output a 1, and you're allowed to query the variables. So the best we have for a lower bound is square root of n here. It's the simplest problem. And yeah, I'd like to know, I'd like to understand whether the true answer is omega of n. Yeah, so why do we care? Maybe I should have said that in the first place. So I think I said this before. So I think of pseudo-deterministic as almost the same as deterministic. And so it still kind of pinpoints something explicit for you, but it's since a relaxed notion, maybe we can speed up, or come up with constructions where we couldn't deterministically. And the second reason to care, which was, I think in the original paper, and I didn't really understand it until Russell helped me out quite a bit, was they were motivated by the idea of reproducibility or the replicability crisis in science, where you can think about it as applying to scientific experiments or machine learning algorithms where you have a bunch of data and you output some hypothesis or you output some learning algorithm and somebody else wants to replicate it. And if the algorithm or the process involves a lot of randomness and replication, one way to define it is that somebody else can come and get the same result, the exact same result. And so pseudodeterminism was inspired by that idea of trying to do something that's replicable. So I'm going to talk now about this notion of reproducibility in the context of learning. And again, it's a modification of the definition of pseudodeterminism for reproducible learning algorithms. Yeah, I think I'll skip this. So the basic punchline here is that there's this, I don't know too much about this, but this reproducibility crisis, which has been around for a long time, which, you've probably read lots of articles about published findings that can't be reproduced, and sometimes they're false and sometimes they're not, and sometimes it's not known whether they're false or not. And the reason, one of the reasons, I don't know how to go backwards. One of the reasons is that, when you do an experiment, and what you're supposed to do is ask your question, collect all your data, check to see if make your hypothesis, collect your data, check to see if your hypothesis, is statistically significant. If it is or it isn't, drop the data, ask a new question, collect new data, and so on and so forth. And of course, people don't do this because data is very hard to generate. So people tend to use the same data on the second round of the experiment, third round, and so on. In machine learning, the same thing happens. We reuse the data to fine-tune parameters, and that can lead to results that don't generalize. So this new notion of reproducible learning is a way to sort of force a learning algorithm to collect data, but produce the exact same hypothesis with high probability. And I'll give you a flavor of it, and just to tell you that when I started this area, when I started working on this, Russell and his students had already had this definition, and I thought surely it's a great definition, but I thought surely there's nothing that one can do in this model, and I was dead wrong. So I'll tell you about some, bunch of algorithms things that you can do reproducibly. Any statistical query or statistical learning, heavy hitters, approximate median learning, finite concept classes, and so on. And most recently, it turns out that there's a very strong connection to differential privacy that I'll hopefully have time to describe at the end. Okay. How much time? Oh, good. Okay, so let me just define it for you. So let D be a distribution over some universe X, and then and think of A as a learning algorithm, but it doesn't have to be. So if you think of it as a learning algorithm, A takes samples S from this underlying distribution D. So think of it as M labeled samples of some, concept. And it also has random bits R, which you can think of as like a way to set the hyperparameters or who knows what. And we'll think of the algorithm as, a learning algorithm. So it should output a hypothesis that, with high probability, generalizes two samples from the underlying distribution D. And so normally you don't put any reproducibility requirement on the algorithm, but we want to say a learning algorithm is row reproducible if for every distribution D over X, and for the probability where you fix the random string R, and then the probability where you take two different samples, S1 and S2, that the algorithm produces exactly the same hypothesis is at least 1 minus rho. So you can think of this as for most R, the algorithm A outputs the same hypothesis for almost all samples that you give it, okay? So to me, that seemed like really strong. How would you ever expect learning algorithms to do that? Yeah, so I'll show you that I'll show you some examples of this. Good. Okay, I want to just mention some related notions. Yeah, so the normal definition of pseudodeterminism, it was not designed for learning. So the normal definition, you have the input X and you have the random string R, and there's no samples. So you're pseudodeterministic, like we said before, for every X, there's a particular Y that's almost always output. So the difference between these two is now we have samples. And there's a notion called global stability that that came up in seminal work relating different approximate differentially private learning to Littlestone dimension. And in that work, they defined a notion of global stability, which is similar, except that the algorithm is deterministic. So global stability takes samples, and it's supposed to output a hypothesis H, the same hypothesis H over all the samples. So the difference between global stability and our notion of reproducibility is we have this extra randomness. And it turns out that that's really is what is giving us the power. So to do things globally in a globally stable way, typically this delta is extremely small. It's like 1 over a polynomial. And then the third definition, called pseudoglobal stability, this was defined around the same time as our paper, but we didn't know about this work. And this is basically the same as our definition. So you modify global stability by adding this extra random bits. And then again, you require that for almost all random bits, for any two, for most of the sample sets that you would pick, it gives you exactly the same hypothesis. Okay, so why is this nice? So first of all, it's an algorithmic property. It's a property of the algorithm, and it's efficiently testable. So unlike lots of other properties like differential private, testing if something's differentially private is not trivial at all. Whereas this is easier to test. You can just run it and check to see that it almost always outputs the same hypothesis. It's distribution independent, so it's a guarantee no matter what distribution the algorithm is given. And we'll see again that what I said before, that this private randomness R is, we're going to really leverage that to help us. And works no matter what the output of A is, and we can amplify the error row, or we could reduce the error row, amplify the success probability. And reproducible algorithms, learning algorithms also generalize. So these are some nice properties that it has. So I'll just give you a flavor of some of the ideas behind it. Okay, so the first thing is I just want to do a statistical query, simulate a statistical query. So D is a distribution over domain X, and F is some function from elements in the universe to numbers. So for example, F of X could be the height of a person. And what we want to do, given a bunch of samples from this distribution, is we want to reproducibly compute the expected value of this function. Okay, so the expected height of the people in the population. And again, reproducibly means we take a bunch of samples, we're allowed to use extra randomness, but we want to almost all the time output exactly the same answer. Okay, so what would you do non-reproducibly? You just pick M samples and you'd output the empirical average. And this is not hard to do. You don't need that many samples, but it's always going to give you a slightly different answer. Okay, so one idea is that you could divide the interval. The expected value is between 0 and 1, so you could divide the interval into small interval. Divide the whole thing into intervals of size alpha, where alpha is pretty small, and then you can do the same thing you did before. Take a bunch of samples, compute the empirical average, but then round to the midpoint of the interval that you lie in. Okay, and so for example, in this picture, the red would be the true average, and the empirical average, since we picked enough samples with very high probability, it'll be very close to the red, to the true answer. And then we'll make sure we pick enough samples so that bouncing to the nearest cutoff point, the nearest black line, plus the error between the red and the blue, that'll all that'll all be at most tau, which is the confidence that we want. Okay, so that looks good, except that there's going to be so that's going to work for most cases, but there is going to be this worst case scenario where the intervals that we picked, it might happen to be that the true answer, the red one, is super close to one of those cutoff points. And if that happens, then the empirical one can be on either side. So in that case, sometimes you'll go left and sometimes you'll go right. And so you won't, you won't output the same thing with probability greater than a half. So this is where the use of the randomness comes in. So we'll just modify that algorithm by, instead of fixing these intervals to start at 0, we'll pick a random offset, alpha offset, and then we'll just, and that's going to be how we're going to avoid this worst case scenario. So you pick the random offset, do the same thing we did before, and now with high probability, you're not going to, be the true value is not going to be really close to one of those cutoff points. And yeah, the analysis is just turn off, but it's pretty easy to see that it doesn't do much worse than the original one. Okay, and just 2 takeaways. So we're mapping a large output space, which is any possible number in 0 to 1, to canonical representatives via some randomized rounding, and we'll see that correlated sampling is actually a tool. We didn't realize it, but now we do. I can talk about that in a minute, but that's a really useful tool in this to make things reproducible. And another thing, what you did see is that the use of randomness is super important. It allows us to convert this worst case situation to average case. So I won't tell you about heavy hitters, but again, it's not too complicated of an algorithm, but it does, again, use randomness in an essential way. And so we give an algorithm for reproducibly computing heavy hitters of a distribution. And the sample complexity just depends on rho, that's the reproducibility parameter, and epsilon, which is the error. And the interesting thing is independent of the universe size. So in heavy hitters is hard for statistical queries. So it can do some things that statistical query algorithms can't. I mean, it can do them much more efficiently in terms of sample complexity. And then we use the heavy hitters algorithm to compute approximate median. And this algorithm that we have is similar in spirit to differential private, approximate differentially private algorithms for the same problem. And it has very similar sample complexity. And so the log star of the size of the universe is because of a recursive iterative tree-like procedure. Yeah, so now I just want to quickly tell you about learning finite concept classes, because it's pretty easy. So I want to show that if you have any finite concept class, that you can, even in the agnostic setting, you can reproducibly pack learn with this sample complexity. And it should look similar to the typical sample complexity of learning a concept class except that it has the rho in there. And our proof is a little bit complex. Well, it's a little bit complex, but a proof that is inspired by, I'll give you an intuition behind another proof that goes via correlated sampling. So correlated sampling, is a really powerful technique that was used in the parallel repetition theorem. It's used to prove direct sum theorems. And the idea behind it is that there's like 2 players and they have 2 different distributions, P and Q. But think of P and Q as quite similar. So like their total variational distance is they're close to each other. And what the players want to do, they don't get to talk to each other, but they want to sample from their distributions. And what they want is they want to share randomness. And what you want is that that the probability over the randomness that they output the same value should be, it should be proportional to how close they are in variational distance. So the closer they are, the higher, the probability should basically be 1 minus the distance between the distributions, the probability that they output the same thing. So to reproducibly learn, what you can do is, so first of all, you pick a bunch of samples, enough samples, so that for every function in your concept class, you compute how well that function does on those samples. Okay, so you compute the empirical error, and it doesn't take too many samples to do this. It's log of the size of the concept class. And now if you have two different sample sets where you did this on S and S prime, you can think about the induced distribution. So P sub S is an induced distribution over all of the functions that have error at most epsilon. So over with samples S, we did this calculation of the empirical error of all the functions, and we keep the ones where the error is at most epsilon. Okay, and that gives we can normalize that, and that gives us a distribution over the good functions. Do the same thing for S prime. That gives us two distributions that are close to one another. And then if we just apply correlated sampling, well, just apply, but anyways, the idea is that you apply correlated sampling to pick an F, and with a high probability proportional to how close they are, it'll be the same one. We also have an algorithm for house-based learning. I won't have time to tell you about it, but the one thing that's super interesting to me is that the way that we turned the learning algorithm into a reproducible one, in this case, the hypothesis class is an infinite class. So these tricks we've used so far with finite classes won't work, but there's this really beautiful work, this Foam's paper, and it gives a technique for rounding all the points in R to the D to Z to the D with a property that nearby points in L2 space will be mapped to the same thing with high probability. And we were able to use that in this algorithm to turn a learning algorithm into a reproducible one. And then quite recently, this GKM paper, the same paper I mentioned before that introduced the same definition of ours, they showed how correlated sampling could be used to show that if you don't pay too much attention to the parameters, which aren't very good, that approximate differential privacy was already known that is that and Littlestone dimension are related in terms of their sample complexity, and they're also related, and they're also equivalent roughly to reproducibly learning. So it was a real surprise to me that basically they're almost the same as approximate differential privacy is almost the same if you ignore this exponential difference in sample complexity. They're almost, so reproducible learning is actually feasible, at least theoretically feasible. I don't know about the actual practice that Sylvia was talking about, but okay. So I think I don't have time for my open problems, but I just want to say mention one thing. I think it's really interesting that correlated sampling comes up in all of these things. And I would like to understand better the inherent relationships between parallel repetition, direct sum, sampling, and correlated sampling, foams, and reproducibility. I know that sounds like a lot, but I think there's a real core there's a lot of commonality there that we're exploiting, and it'd be nice to really understand it better. Also, we don't have any idea about the computational efficiency of reproducible learning, so that's another area. Yeah, I think that's it. And back to the beginning. Thanks.
Great talk. Any questions? Yeah, there's a question there.
Thank you very much. It was very interesting. So one thing that I didn't catch, is it a proper algorithm or improper?
Yeah, it is proper.
I see.
Yeah, we're taking every single function in the concept class and estimating its error, and then we're going to output one of those.
Thanks for a great talk, Tony. Quick question: what do we know about the dependence on P? Does it have to be
on row?
Or row? Yeah, right. The parameters.
Oh, you mean for the
whatever you can computation or
does
it have to be polynomial, or can it be
usually like a row squared in the denominator typically.
But do we know that that's necessary?
Yes, it's tight. I think we do know a row is tight. One of the rows, right? Yeah, Russell has a question or an answer.
Of course, you can ask the question about reproducibility or replicability. We haven't decided on the name yet, for a lot of different contexts. But the simplest context is the statistical query. And for that, we have a tight lower bound that shows that you need a factor of 1 in row squared.
Thanks.
Ravi?
Your definitions require generally exact equality. If the algorithm outputs a real valued, especially real valued vector, then is there some general way to deal with that? I mean, you had dealt with it by quantizing for the median, but more generally, high dimensional real valued vector as an output, then your requirements are fairly strong for equality. Yeah.
Right. Yeah, that's why I was so surprised. So even for this half space learning with large margin, yeah, we do meet the guarantee that output's exactly the same and it's continuous.
So I'll take my privilege as what's approximate DP?
Oh, so approximate normal DP, you have one parameter epsilon, and you say that for nearby databases, basically the difference between them has to be like e to the epsilon. But for approximate, you have two parameters epsilon delta. It's like probably approximately correct. So you can ignore the tails with probably for all, but with probability at most 1 minus delta, this condition's met.
Okay.
So the really rare events you can forget about.
Thank you. Thank you very much for a great talk, and we have a break.